Welcome back to the deep dive. Today we're not talking about whether large language models can, write a poem or make a cool image. We're going after a much bigger question, maybe the biggest question for AI in the real world. Can these things actually handle serious long-term work without, without failing catastrophically?
That is the ultimate bottleneck, isn't it? We know these models have these remarkable bursts of intelligence, but look around us. We're surrounded by achievements, skyscrapers, global supply chains, financial systems that all rely on doing things right, step after step after step.
Yeah.
You ask an LLM to chain its skills together for, say, hundreds of thousands of steps, and historically the answer has been a very loud no.
And here's where the problem it crystallizes for you. We have this tiny persistent error rate, even if a model is 99% accurate.
Which sounds great on a benchmark test.
It sounds amazing, but you have a process that needs 1,000,000 steps, and that 1% error rate means, well, theory suggests the whole mission fails after about 100 steps. That level of failure just isn't an option for anything important.
It creates what you could call a reliability wall. We've been so focused on making them more intelligent, but we haven't focused on execution at scale. And that's why this requires a totally different way of thinking. So instead of just chasing bigger and smarter single models, the breakthrough we're diving into today, a system called Maker. It represents a completely different path. It shifts the focus to robust principles, decomposition, error correction.
And Maker solved a task that needed over 1 million LLM steps with 0 errors. 0. That's an incredible claim. We won't unpack the acronym just yet. We'll get to the maximal agentic decomposition and all that as we go.
The critical thing to grasp, though, is that this is an orthogonal direction for scaling AI. It's not about scaling up the model's brain power. It's about scaling up the reliability of what it does.
Okay, so every story needs a villain, and for us, that villain is the long horizon task. Let's start with section 1 and look at the test case they chose, the Towers of Hanoi.
The Towers of Hanoi, or 2H, is just a perfect stress test. It demands sequential, dependent logic across a huge number of steps. It's that classic puzzle, right? 3 pegs, a stack of disks. You move one at a time.
And you can never put a larger disk on top of a smaller one.
Exactly. And the number of moves you need, it scales exponentially. It's that 2 to the power of d minus 1 formula.
So for a small number of disks, maybe 4 or 5, an LLM can kind of muddle through. But the sources show that as soon as you get past 5 or 6 disks, the performance just falls off a cliff. It's a catastrophic failure. The process gets derailed after a few hundred steps, max. One mistake, and the whole thing is ruined.
That's it. And see, most traditional benchmarks, they test independent examples. Model gets 99% on that, and we say problem solves. But when you need to get 1 million steps right in a row, 99% accuracy per step is actually a guarantee of failure. The target task for Maker was 20 disks. That requires exactly 1,048,575 moves.
It demands a system that's designed for failure, not one that just tries to avoid it. Which brings us right to section 2, the core philosophy here. Massively decomposed agentic processes, or MDAPs.
This is the architectural leap. Instead of one giant brain trying to reason its way through everything, you break the huge task into millions of tiny, simple pieces. It creates this modularity that lets you spot and fix errors really efficiently. Maker is the first working example of this, and it shows a huge multi-agent advantage.
Okay, I have to push back a little here because that sounds completely counterintuitive. You're telling me that breaking a 1,000,000-step problem into 1,000,000 individual microtasks makes it more reliable. Doesn't the coordination overhead just kill you? And you've just created 1,000,000 new points of failure.
It's a fair question, but that's why the maximal agentic decomposition, or MAD, is so powerful. We're not just breaking it down a little. We take it to the extreme. Each agent only focuses on a single minimal step.
So M equals 1. One agent, one simple move.
Precisely. And the benefit is twofold. First, we know from tons of research that LLMs get less reliable as their context gets bigger and more complex. So by limiting an agent's context to just what it needs for one step, move disk 1 from A to B, the error rate for that step plummets. Second, and this is huge, it means you can use much smaller, cheaper LLMs. The complexity is now in the system's architecture, not in the individual model's brain. So you just need little focused models for the microtasks.
All right, I'm sold on the decomposition. But now we have 1,000,000 potential, albeit smaller, points of failure. Which brings us to section 3, the really clever part. How do you correct 1,000,000 potential failures without it costing a fortune? This is where that first to ahead by K voting comes in.
This voting scheme is what makes the whole thing work. It's what gives us that incredible scaling. So for any given subtask, like figuring out the very next move, you have multiple agents generate a possible answer. You keep sampling until one specific action has been suggested K more times than any other action.
So K is your margin of victory. A big K is more expensive but super reliable. A small K is cheap but a bit risky. But the math here is what's so fascinating. If the problem's difficulty grows exponentially, but the cost to fix errors only grows, log linearly, that's almost like getting reliability for free. Can we pause on that?
This is where it gets really interesting, and it just completely changes the conversation about scaling AI. The sources prove this with scaling laws. They show that the minimum margin you need, your K-mine, to hit a really high success rate like 90% success for the whole million-step task only grows logarithmically with the number of steps.
Logarithmic growth is, it's practically flat compared to exponential growth. It's almost laughably slow.
Exactly. Theta log iconos. It means if your task suddenly needed 1 billion steps instead of 1 million, your K might only need to go from, say, 3 to 4. And because that required margin grows so slowly, the total cost to solve the whole task scales really efficiently. It only grows log linearly with the number of steps. That's theta ester log s.
Which means the system's cost behaves like a classic efficient computer algorithm. That is completely different from the exponential cost we usually see with complex LLM jobs.
Precisely. And to make this concrete, you mentioned the cost. Early estimates for solving the 20-disk task with many of the big proprietary models, they were projecting costs over $40,000. They just couldn't handle the error rate without brute force.
And the cost using the Maker framework was?
Using Maker, they could pick a super cost-effective model. The paper calls it GPT 4.1 Mini, which sounds like a special variant they used, probably tuned for this kind of low-context, high-speed task. With that model, the projected cost was only $3,500.
Wow, okay, that difference, 40 grand down to 3,500, that's the real-world payoff of log linear scaling. It shows that Maker lets you optimize for cost and speed because you're fixing errors with the system, not by paying for a supposedly perfect giant model.
You get to pick your model based on its cost per single step, not its grand reasoning ability.
So we've broken the task down. We have this incredibly efficient voting system to catch random errors. But you said there was a third component, red flagging. If the voting is already so good, why do you still need to throw away data?
This is so critical. It's because of correlated errors. Red flagging is simple. It's based on the idea that when LLMs mess up, they often show predictable signs of it. So Maker just proactively discards any output that looks risky, especially the kind of risk that could fool the voting system.
So what tells you an agent is, having a bad day? What are the main red flags they look for?
The first one is just overly long responses. If you ask an agent for a simple move command and it starts writing you a novel with its internal monologue, that's a huge warning sign. The experiments show the error rate increases precipitously, are their words. Once a response got over about 700 tokens, the agent is basically stuck in a loop, overthinking itself to death.
It's signaling its own confusion.
Exactly. And the second flag is formatting. If an agent gives you an answer in the wrong format, that's highly correlated with confused logic. Instead of trying to have some fancy parser fix the output, Maker just says, nope, that's garbage, throws it out, and gets another sample.
Okay, so why is this so vital? Why is getting rid of these correlated errors the key?
Because the entire voting system is built on the mathematical assumption that failures are independent, random events. If several different agents all fail on the exact same step in the exact same way, that's a correlated error.
Then the voting mechanism will just pick the wrong answer confidently.
It'll confidently ratify the mistake, and your whole process goes off the rails. Red flagging is the system's defense against that. It protects the integrity of the vote.
That makes perfect sense. The whole design is for independent failures. Which brings us to the payoff, the triumph and broader implications.
And the results were definitive. Using that tuned GPT 4.1 Mini and a really low voting threshold of KRIM equals 3, Maker successfully solved the 20-disk Towers of Hanoi problem. Over 1 million LLM steps, 0 errors, and the system proved the theory. The number of steps that were still undecided just dropped exponentially with each new round of voting.
So the cost is all front-loaded. You pay for those first few rounds of voting, and then the system basically just sails through the next million steps.
Exactly. The vast majority of the cost is in those first 3 samples per step. The rest is negligible. It was a perfect practical demonstration of that S log S scaling.
What I find so interesting is the parallel the sources draw. This isn't just an AI architecture. It's a mirror of how human engineering has evolved.
It's a perfect parallel to the software industry's shift from giant monolithic applications to microservices. When you break down a single agent's huge task into microagents, you get all the same benefits: modularity, independent scaling, and a design that's built for failure from the ground up. Natural language just becomes the communication protocol between them, almost like an API.
And finally, let's touch on the safety implications. If we start relying on decomposition instead of just raw single-agent intelligence, what does that mean for the risks of advanced AI?
It limits the blast radius. If you can reliably break down big problems, then any single LLM's influence is strictly limited. That makes things like sandboxing, auditing, and control so much more effective. Since most of the work is done by these smaller, focused models, you avoid some of the risks of constantly building bigger and smarter single-agent models. The sources suggest this could help mitigate superintelligence risk by limiting the scope and autonomy of any one agent.
So Maker seems to prove that reliability and scale in AI don't just come from throwing more intelligence at a problem. They come from applying these time-tested computational principles: organization, error correction, decomposition. It's a shift from a raw intelligence score to organizational robustness.
It shows that a reliable organization of medium intelligence parts can totally outperform an unreliable single genius.
And here's the final provocative thought we want to leave you with. Since Maker's cost scales so efficiently and it relies on these small, almost non-reasoning models for the actual execution, does this completely shift what we even mean by superintelligence? I mean, are we moving away from the idea of AI as a single, giant, unreliable brain and toward a massive, reliable, error-corrected organization of microagents? This suggests the future of high-value AI might look less like a single genius and more like an extremely efficient, highly auditable supply chain.